Hello everyone and welcome to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you like to follow along, please don't hesitate and be welcome. Today we will continue making this awesome debugger, and if you like to ask me questions, you can post them on Twitter or YouTube and I'll be there to answer. I already opened the project. Oh no, seems not. So let's open it. Alright, and if we go to the last thing we did on the last stream, was that we continue making the assembler, and we had some more usage here for immediate modes and for some rate control, that use the mothering by. So yeah, I mean, this is the idea. We have to fill out the whole set of instruction in here. So yeah, so let's see if we can fill out some others, and yeah. So let me go back onto the here you go. We have these are the subscripts, which are the ones that define the addressing mode in this case. So we can take here, for example, oh no, actually we didn't run it, you see. Let me compile. We do compile. So let me run this first, because I remember now that we set up an instruction thing here, where we have we dump a simple instruction. I mean, there's not too much into it. We can even do it right now. Dump. Let me see if I have it. There you go. So this is the whole thing. We have an XOR and a call to the exit process. So if we run this, that's it. There's nothing to it. It does the thing and it runs that. So I mean, we have a correct executable. So now I would like to go and inspect it into the debugger. Right. So let's see, I mean, across the whole set of things that we already written, I would like to go straight on. Where are these things? Well, it doesn't matter. Here we extract the data directories. I would like to start over here. There we go. We initialize the disassembly state, which we say, hey, have pointer to raw data. So we have this assembly state, and we have an arena which we haven't initialized at all. We have the Kurinako by, and I can look at it. Oh, okay, yeah. I was like, what? Yeah, here's the 0305E82F00. These are the instructions. I was like, well, yeah, but the point here is that the segment is a little bit wide, even though we have just a few instructions in here. This is the XOR, I believe. Probably this is not the XOR, which is, we have a bunch of 6 yeah, we have a jump to start, which is the first one. This is a jump start. We have a bunch of CCs here. We have a 33C0, which is the XOR. So the 33C0 doesn't have any immediate thing. It's just the operand and probably the motherand. And then we have 03, 05, 08 to F0000, which is our instruction. We have the operand. We have the motherand here, and the immediate or the offset. If that makes sense. So we like to do, yeah, I mean the inquiry that we had is like how well we know that there's some place where the data is going to be fetched, you know, um, and probably, I mean, I'm not truly certain about it, but I mean, if you see here, this value here is totally different to this value. We are certain about that. So, 2f8 is nothing more than 12,264 bytes. We have to move 12,264 bytes upper on memory to find out data section. Load it into memory, of course, which we don't have it here. So, and this is something totally different. This is the relative address based on the value once it's loaded into memory. Yeah, it's like an RVA. Well, basically, this virtual address of the element we're trying to access. So this has to be somehow translated. I mean, we have to find out this based upon this information. Now, how do we have to do that? It's an interesting thing, because I mean, if we see on the data, I would like to go to the data section. So what if let me try to do that. I will write some code about that. So let me put it over here. Reset. Now, yeah, I mean, there's a reason why it's different, because you think about it. I mean, the instruction has to fetch it, but the instruction, I mean, this value over here has to be read from. I mean, the instruction has to read it, you know, whatever it is. We have an instruction pointer which we are thinking is not used at all, but this is the offset, you know, and we go back here. So if you think about it, I mean, these values, I mean, EAX has to be a value memory, you know, it has to be a virtual address. Because it's the effective address, you know. So to solve this problem in conjugation, what I have to do is to test it, you know. I will go to the data section. Where is it? This is gonna be text header. This is gonna be data header. There you go. And I would like to gather that. Now what I'm gonna do is something pretty similar to this, yeah. And this is gonna be based, oh my god, something like this. And we got that. So that's gonna help me to find out more about the information that we have over there. So around this, and around this, you know. I don't care about that, I don't care about that. I want to see this. You know, we are on the data. The size of row is 412 bytes. The virtual address is 16,384. Put the calculator, and we have 12 to 64. So it's not gonna get it there, you know. So we have data pointer. Well, we have a pointer to data. This is a file pointer, you know. So we can find it on the file itself, not whenever it's run. And that's the reason why I want to be certain about it, you know, because if that's what we want, I mean, this is the closest, this is the real meaning, isn't it? Because this should go, I mean, we need an offset from the base of the place where it's loaded to the section to the place whatever it is, you know. So I mean, how can I say this? Data pointer. I want to copy them. And this is C. Yeah, this is a 28. Now this is in memory. Sorry, this is in the file pointer, you know, which is good. I mean, we got to the point where we found it, but in real, I mean, when the process is running, my question is, how does the offset that we see on the value on the instruction is interpreted, you know? So we have a virtual address, but this doesn't tell us too much. I mean, it's pretty close, but it's not the thing at all, isn't it? And this is not the thing. It has to be this 12 to 64. But if it's 12 to 64, then the virtual address of the first byte for that data section is on the 16384, it's not gonna get it. So something else has to happen before looking into it, you know? Oh my god. Because if you think about it, we have 16384, you know? I'm gonna copy this here. We have 16384, and then here I have we have text header, and this is on the virtual address 4096. Okay, so it's aligned to a page boundary. So we have 4096 and we have 16384. So if we take the difference, yeah, we have to move 12 to 88. Now we're pretty close, isn't it? So what if I mean, but this is because we are on the first instruction, but we are not in 4096, because if you think about it, it's gonna be loaded contiguously. So based on the instruction, we are gonna be in 4000 something bigger. So let me go. How can I do this? EagleFly. I wanna load the test build listing, and I wanna see 000002. This is totally busted, man. This is gonna be better, you know, because we have, you know, this is 00, 1, 2, 3, 4 bytes, 5, A, so the real instruction is on the 12, you know, this is on the 12 hex. So we go on the 12 hex and it's 18. So we move this, you know, plus 18, and then we have 12 to 70, which is something. We're close to it. So probably, I mean, this is telling me that this is more like a relative address. You know, it's based on the instruction pointer, which is something that we didn't expect. Yeah. We have 16384, and we're moving for 4096 plus 18, which is to the instruction itself. But instruction pointer is gonna be already past once read, isn't it? So it's gonna be on 18, I believe. I don't know. So if we move (24), it will be too much, isn't it? 12 to 64. Oh yeah. Here you go. So yeah, I mean, this is the thing. So this is the value that we were looking for. 12 to 64. So that's gonna be the value that whenever the loader loads both segments and get aligned to page boundary, they get loaded. Whenever the EIP runs into the instruction and executes it, it's gonna go pass back to the next instruction, and from there it has to read the offset and move 12 to 64 bytes up in memory to fetch the data segment with the data information that it needs to execute, to load. Interesting. I mean, that was my first guess. But I was like, well, I mean, they never tell me about EIP, because EIP, it's used explicitly, I mean, right now we are using it explicitly on 64, and that's because we are in 60. I mean, probably it's because we are in 64. I don't find any other reason why this happened. Because if you think about it, I mean, on 32 this couldn't be possible, because we're using normal registers. I mean, the only way for it to be possible on 32 is if we're using control registers or something like that. But we're using normal registers. We are adding EAX to an immediate value, Well, we are adding the immediate value to EAX, to be more clear. But that instruction happens to be instruction pointer relative, which is interesting. I don't know if all of them are the same or all of them are looking. So probably what that means, I mean, if you think about it, is that, and probably, I mean, I haven't played too much about it with this, and that's good, because I mean, I haven't played too much about reading. For example, that's one of the nice, probably in this case, the bad things about working with macro assemblers is that you don't have to care too much about that if you just use values to extend it. I mean, I declare here a value in the data section, and then I can just use it making that reference or using that mnemonic. So yeah, I mean, that's the problem. I mean, if we want to be really, 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 really picky and understand it, we will have to do something special here, where we define, where is it? I mean, instead of defining, the value I want you to define, it's somewhere in memory where it's gonna be inside the data section, and this is blah 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 stuff. That's something that is hidden even in assembly. It's hidden. I mean, it's something like, whoa, how is it? I mean, how is it encoded? How do you get it? How do you get the value from the data section? And and there were two possibilities. I mean, one possibility would be that is relative to the base pointer where the executable is loaded. Like the base of the image, which is more reasonable. I mean, something that I was expecting. But no, it's instruction pointer relative. So we have to go to instruction, one pass back, and from there read the dimension, read the offset, and go directly to the data segment. Okay, that's good. Now I would like to run this exact example on an x64 architecture, some emulator or something, to see what happens. I mean, this would be totally different, isn't it? I mean, they are the same instructions, but we cannot do that on x86, I believe. I mean, for now, what I've seen, it's something that's possible, but so yeah. So we have a relative address value used. So with that case, yeah, so now I have an idea of how to decode it. We just move from the relative address where we are looking at and move back. We'll need just to go some data information, whatever it is. And you think about it, well, it will make sense to add this value over here. I'm gonna copy that, and then move a little bit upper, pretty much something like this, plus 2f8 we're located in that hex, and we have 0108 oh 2f 12 to 64. Okay. Well, probably it's because this is in hex. Alright. And this is alright. Oh yeah, it has to be this one. I'm sorry. I'm really sorry. There you go. So yeah, this is basically we have to do this to the compute and find the address. We have blah 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 1400400, which is this one, and just write it. Okay, pretty straightforward. There was no magic other than summing up the values, of course. Yeah. So that's pretty much it. So we can implement that. Oh my god. So we can go here. Have a direct address. probably what I want to do before this. Okay, so we're gonna define a mean bound, max bound thing, and probably whenever we run this is the perfect thing. I wanna, I wanna say something like the address value. So that's something here. We can say we care about the virtual address, so we have a text header. Hold a second. Put the charger. Now the virtual address is U32. Probably that's the reason why we have 0 zeros on the other side. Where is it? How can I print a hex value? Something like that, I guess. Now where's the 4? We'll have it here. This is a for loop to get the sections. We start this assembly here. So we don't have any for loop, or we take it out, I guess. Yeah, because this is for the mnemonic, and this was the code segment side. Yeah, this was the thing that we were making. We were assuring about it. So probably let me take it back, and I'm gonna move this. We don't care about the prefix, I guess. So I'm gonna say something like this. Alright, and I do care about this section. I'm gonna say where is the print? There you go. So we print it back, and all this data has to be inside. So we move it to here. Now I want to see it for myself. Yeah, that's the for loop. And this is the other for loop. So yeah, that's correct, I believe. Yeah. Alright. So once that I match that, and we are in a for loop here, so we're going to rate by code 7 size. Now I want to be sure here that we control everything with instruction pointer, because I believe that's better. So we're gonna print out this, we can make it different later, but for now it's gonna be simple. Where is it? Over here. I want to move this because since we're not using, it's just making space. Just want to put it here. I put this in here. So we're gonna first print instruction pointer here. Now back in, that's not gonna work here. I'm gonna use system state IP. System state. Put the system state virtual address, good 7 size. There you go. We're gonna be printing. There you go. I think I like it that way more. And we need to print the opcode bytes pretty much the same way. So I want to cache this. I'm gonna probably the mnemonic and all this stuff probably can go out. Now I can say, what if this is the text, so it's I can just print them out. Push drag. I'm gonna decode it. We got the mnemonic, the text. Sorry, we can do this in the first pass, then we go for each operand and we find it out. Here we're trying to print also code bytes, so probably for example, here I'm gonna print each one of the, I'm casting here a lot of times, but yeah, I have to be careful about how many pointers we have right here. But for now, I want to simplify this, so I want to say something like we know the mnemonic, we know which type it is, we know which so probably we can work this like a 2-pass thing, which is, I think, something more. In the first pass, we're gonna find the size of the thing. Of course, I mean, we can do both on the same thing, but since we are, if we know the size, we also know other things. Like for example, in this case, right? Once we know the we got the table now, isn't it? And we got the operand. We know the operand. Well, we know the mnemonic, and we know the operand count. We don't know anything about printing it out, so we cannot print too much about it. But the mnemonic, so the mnemonic can go out, it can go until the last stage, I guess, and say, hey, I'm gonna print it up here, do wherever you stuff you need to do. Yeah, I don't care. So we're gonna do something like that. We got some information here, in this case, special case scenario. We have the operand, the mnemonic operands, operand index, switch, operand address mode. And then we're gonna go straight on. And let's say we're gonna print the bytes, which we're looking at here. And image buffer, cby, where is cby? Where is 1 byte opcode? I'm gonna do it like that. I'm gonna do like this. But yeah, probably, yeah, this is important as well, because this is in file. Yeah, I wanna call it different. I'm gonna call this file pointer. Yeah, because we're running into, we're imagining we have to define the virtual addresses that are the ones specific for the instructions, and the file pointers, which are the ones we are looking at. So we have a file pointer opcode. Probably this is current pointer. Current file pointer base. And this is current file pointer byte. Current file pointer back, current file pointer back, current file pointer back. So we have a file pointer bang. I think that's more clear. And this is the file pointer bang. We decoded, got it. Now we don't have 1 byte opcode at all, so we're gonna use this asm stay file pointer bang was 1, and we'll reuse this. So, well, we can do this. Go to file pointer bang, and then have a car, and then we're moving up here. We have the image buffer, this has some stay. We don't have mother ramps, so we just printed them out. Okay, we print them out, and we can say, hey, what if we say this? Now, yeah, and then we can some assertion here. So we're just printing them out as well, which is good. I would like to have a concise meaning here. So probably I'm seeing something interesting. What if we do this? We have something like this. Thanks, we have that. Let me try to do it this way. So let me be more expressive about what I mean by this. I don't know if you see it right now, but I'm just trying to, I can call this define an API. Now at this point, I want to well for mnemonic information. So probably what I want to say, it's probably do I have an instruction? So this is gonna get us to the opcode bytes, which they have to be found. I mean, this process here has to get us to there, and the mnemonic can be something like that. And what else do we need here? Let me see. Since we know the type, we know that there's an immediate, we don't have mother RAM, so we can say that over here so I feel more like that, you know. And this has to be implied here. Probably we're moving, yeah, but because the system state has to be uploaded with the decoder. So I want to say more that explicitly, so we can say something like this. I can put it as a pointer. Yeah, I believe it's better as a pointer. So I can pass it like this. So we know we're gonna modify that. And got the instruction of table mana. The table, we're gonna do something special with that. Right now we don't care. We're gonna operate onto that. We got the instruction. The instruction is gonna hold basically the whole thing. You know, it's gonna make the work of this thing pretty much basically. So we have to here we decode each operand, which is okay. That's good. So now over here it's just like, hey, instruction size plus equals the operand. In this case, type and we have to have, well, we're moving the size so we can print them all together, all the opcodes along its way. And we probably want, we have the operands, we have the instructions and its dimensions. Okay, I believe we could break if to this. Well, no, because there's another operands into it. It can be, you know, just as this one, if you remember. I mean, this is a 2 operand, so we decoded one, but the other is EAX, and EAX is encoded into 05. You know, we have a mother M. So if we go to the addressing mode rec control, the rec control tells us that there's a mother M. We have a control register on the rec field. So we have a mother M C by. Sustain C file pointed by. get the rect field. Can do that, and then you move it, you get the rec, and then from the table we are moving up from the rec field on the dimension and the operand tag to get the name, and we print the name. So probably we want this, an instruction, probably where is it? Now we have two options here. Normally it's a register or it's memory. If it's memory, we have to find about some extra information, pretty much the offset, I guess, because the register, we find out that the value it's EAX, so we can have a pointer and we just print it out, say hopper name, print names, or so we can say can do something like that. Now, I mean, this is gonna work because this is a nullify string. So we can, yeah, this is the caveat. We have to think about, well, we can have that as a must, but probably we want to do something better later. So we push the name to the buffer so we can print it down. What else do we need here? We know that, yeah, this is gonna encode that. Of course, this is gonna be a control one. So we basically want to have, well, now I don't remember. I mean, there were 16 control registers on the biggest one, so we probably want to have 0, 0, 0, 1, and right now I don't care too much about encoding here, but I don't know. How do we encode 00? Oh, it's because of the encoding, isn't it? I mean, if we see the table, we have. I mean, we have explicitly telling you that hey, this is 00, blah 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 blah. So yeah, and with extended registers, it's gonna be something like this. You know. But well, I'll keep it right now for this. I'm gonna see this later whenever we define the API. So first, well, we started with this. We started with push it. Yeah, we got it from there. Break name stable. Blah blah blah. Yeah, we had it. Open type. Blah blah blah. So this is a control one. So that means that we have a register field, and we have blah blah blah, and the register field is gonna have a value. You know. And the operand type, we have the type has to be already encoded to get a reasonable value into it. So the problem is that since we're using a array control here, we probably want to define here. We can even define it like this, or register control. So we want from the control register, and the rec field, it's known because of the value that it has, because you are choosing by the groups. So if we look at the groups inside table, this is the model range. So we have EA, EC, ED, yeah, it's gonna work, I guess, as a value. So the rec field is gonna select something valuable in there. We just need to care about choosing the right column in our table. So we have right control to modify that. So the type, probably the type can be a right control, but the encoding has to know that. But the encoding cannot know that at all, because this is the thing that's telling us, hey, this is a register control. You know, it's not like, hey, you're gonna tell me what something. Sometimes it is, but we cannot assume that. So we probably, it's better to have it as an enum. So where is it? I can say, where is it? Because we have types. I want another here. Fly register types. So this is gonna be rec type control type extended control debug extended debug. You can have a byte word can be, I can call them 8-bit registers, 8-bit rec type 8-bit, 16-bit registers, 32-bit registers, char EAX, stuff like that. What else do we have? We have M0, 64-bit registers, XMM, and then I put the racks, which doesn't matter. These are 64-bit, but this is, well, I'm gonna call this 64-bit. These I'm gonna call them MMX. So 64-bit extended control. So you got the put it here. So we do something like that. If we do something like that, we'll need to do, we have write control, write type control. There we go, and we go to that. Push name to the buffer. For now, we don't got standard, but you can say this. So we don't have a quirky bug busted here. So we have a push name to buffer. Okay, that's good. And probably so it's until this point that we know that this is a control register that we are looking at. So that's the reason why we go and find the name, we push the name, and if we go here, we select the control register as well, and we need the size, isn't it? Because, well, yeah, because it's gonna tell me, hey, C. I mean, let's find something with C here. I don't see anything with C. CLC, STC, no. Yeah, because these are very weird axes. It has to be system management mode, I believe. LCC. S. Okay. LCC, what's this? These are the extensions. Which are all these tables. These are the scale constructions. Which are other tables as well. Escape. Okay, I got you. Okay, look at this. This is the thing that was missing. Well, we already know this, but let me see if there's extension with this. Oh, and this is interesting. We didn't know this, but whenever if we use the W extension and we were working with let's say 16-bit data operations, the extension works make it well if this is 8-bit. This is 8-bit and this is 16-bit. So this 16-bit use the extension REX. But W field, where is W field from? I'm assuming it's the REX W field. Isn't it? Oh, look at this. Oh, yeah. So these are the ones. Some of them are reserved, so we cannot use them at all. Well, that was good because we don't use it in any case, I guess. So we have debug registers. Okay, the DTN field it's inside the opcode by, which is on bits. It's DTTN. Oh, look at this. Now we know the our assumption is already solved. So direction bit tells us practically the way that we have semantics, you know. Direction works with semantics. Which is the source, which is the destination. Look at this. This was the extra information that we were missing. Well, at least we know. Okay. So there's a lot of information here that we have to take a look at. But we have to go slowly with that because we have to finish this stream earlier today. So yeah. So first, let me see the compilers because they're gonna be a lot. They're gonna be a lot. We have yeah. C-field, C-fob, point base. It's not a member, but disassemble is the C-fob turbine. C-fob pointer base. We have that. We have that. We have that. And we need this is gonna be size D, and this is B. probably mean the base, file pointer base. These oh. Okay. So I mean this is totally stupid, I think. Yeah, because yeah, let me change this back. I'm gonna do this as file pointer. So uh mm, current pointer, current file pointer by and just want to say this a little bit clearer. This has the current file pointer base, code segment size. This is going to be file specific, so we don't be bananas with that. And instruction pointer, we're going to be moving it by ourselves, but alone, independently. So we do that, and then we're acidic. This has some stay instruction on declare identifier. Well, this is instruction. And prefix list, we don't have a prefix list by now, which we can define. Well, we don't care too much about it. The code functions define arguments. I know we haven't cleared that yet. I haven't worried with that. I know what it's valid pointer. We can define this, not to still know hard deal. Which the whole point of this is just to, since we're gonna be moving for the current file pointer through the whole set, I don't want to run out of the thing, you know. So that's why I'm restoring whenever we are moving into it, you know. So we can do it pretty much easily. I'm gonna go here. I'm gonna find. I can do this like this, and if I this has some state, and this is something, and this the pointer is greater some state current file pointer base, and for this I'm gonna pull file pointer. This is a file pointer base. We're gonna be moving like this, file pointer base, and this is gonna be something more, and file pointer less than or equal. Well, it's gonna be it has to be this has some stay C file pointer base plus system state C file. code segment size. Okay. All right. So let me explore this a little bit more. Running out of time, but doesn't matter. Let me see here. So yeah, I mean, it's because, well, we need to read this to really understand. I mean, it's good. It's good usage code. It's clear what we're doing here. So, but we need to do something more here. For now, it's gonna be okay because we just need to care about pushing the name to the buffer. You know, we're gonna print that thing however it needs. In this case, we know it's a register, so we don't care about that too much. Of course, since it's a control register, we have to follow these rules to really understand it. So we have to do a little bit more quirky stuff inside. But it's not a big deal. I mean, with time and effort, we're gonna get it. So yeah, in this case, it's gonna be the same. But we have a good usage case here. Sorry. So right here, I mean, I have these things, so probably I'm gonna move this like this. The whole point is to print this afterwards, you know, with instruction. I could call this expression something, and then mnemonic. I'm gonna put it in the instruction as well. I can join it back, I guess. So probably, yeah. So we fill it out with the opcode paths, and yeah, okay. And this is IP, you know, and this is instruction, printing out code paths, print mnemonic, something like that. Let me see what else do we have. Brain. Well, this is like this. So yeah, these are the errors that happen to be. So we're gonna leave it that there's like that, so we can see them and continue with this later. So I'm gonna stop here. But hey, we're just in the entrance to really getting into something here. So I think that's good. You know, the more we see, the more we experiment, the more we use this code we do, the simpler this thing is gonna get. You know, and we can do that on the next stream. So yeah, so thank you very much for coming up on this stream, and if you would like to follow along and ask some questions, please ask them on Twitter or YouTube, and I'll be there to answer. With that said, I will end the stream. and I will see you all on the next stream. Goodbye.